You have hopefully finished watching the Tyler video on galvanic cells, and you have a much better understanding of what a galvanic cell looks like and its components. So you know each galvanic or voltaic cell, same thing, right, has two half cells, one with a oxidation reaction going on and one with a reduction reaction going on. And each half cell contains an electrode, and we say that each half cell's electrode has its own standard potential. And if you remember, potential is kind of like a difference in potential energy. And this is why some metals relative to others will become oxidized versus being reduced. Okay? Now, the difference between the two half cells is called the standard cell potential, because what we have is the galvanic cell or the voltaic cell, and we say that the standard cell potential is basically the difference between the two electrodes, the one that gets reduced and the one that gets oxidized. And if you remember, oxidation happens at the anode is oxidized, and reduction happens at the cathode. Okay, reduction happens at the cathode. So you should remember this as an ox, red cat. Here's your, it does not look like an ox. There we go. There's your ox. That's where the oxidation happens. Okay. And then reduction happens at the cathode. All right. Good way to remember it is an ox, red cat, oxidation, anode, reduction, cathode. Okay. Now, we know for a fact, so this is some of the stuff that I already went over in class, and I'm doing it just so you can watch it on your own, at your own pace. Okay. So we know that the half cell's reduction potential, or the potential of each individual half cell, cannot be measured by itself. So we came up with the arbitrary standard hydrogen electrode that has a cell potential or a half cell potential of 0. So we can basically make that the baseline and compare all of the other half cells against it, right? So the one electrode that we set to a potential of 0, this is an arbitrary setup. We had to come up with it so we can actually make sense of what is going on, is the hydrogen electrode, okay? And this is what the hydrogen electrode looks like. The standard hydrogen electrode, or the SHE, is a container, usually a beaker, full of a solution that contains a 1 molar concentration of H plus, and in it is submerged. So this is the 1 molar concentration of H plus there, okay? 1 molar concentration of H plus, and in it is submerged a inert platinum electrode. Since platinum is a very non-reactive metal, it's a perfect metal to help the electrons hang out in the solution but not participate in the actual reaction, okay? So you have the inert electrode submerged in there, and through this electrode there's a little tube, and through this tube we are pumping in hydrogen gas at a pressure of 1 atmosphere. So the 1 atmosphere and the 1 molar solution are what makes it a standard hydrogen electrode, okay? Now, the hydrogen is being pumped through, you can see the bubbles, and what happens at the surface of the platinum is that the hydrogen gas will lose its electrons and become H plus ions, and H plus ions in solution will pick up those electrons and become hydrogen gas, and that's what you are seeing bubbling here. So you have hydrogen being both oxidized and reduced, which basically cancels itself out, giving us a electrode that has a potential of 0 volts. All right. Now, if you plug this in to another half cell, we can figure out, based on what's going on the second half cell, what is the potential of that particular half cell. So here is what it looks like when you plug the standard hydrogen electrode into zinc. Now in class, I feel like I could have explained this a little bit better. So hopefully you're watching this for a better explanation. Okay. So when we connect the standard hydrogen electrode to another half cell under standard conditions, which means the concentration of this solution also has to be 1 molar here. Zinc nitrate has to be 1 molar here. Okay. What we see here is a zinc electrode, and zinc, when you plug it into the standard hydrogen electrode, is actually oxidizing. Okay. Now I talked about how the voltmeters wires can be switched, and that will indicate a difference in sign, and that's because of the direction of electron travel. Okay. So a better explanation for this particular scenario where you have a 0.76 is once the voltmeter has been plugged in, if electrons are traveling from zinc to the hydrogen electrode, that means zinc is being oxidized here. This is an oxidation half reaction. Zinc is becoming zinc 2 plus 2 electrons. Those electrons are traveling to the hydrogen. Okay, so the oxidation potential of zinc is positive 0.76. Okay, this is for the oxidation of zinc. If zinc was being reduced, if you flip the wires, if zinc was being reduced, then the sign would be changed to negative. Okay, so for the oxidation of zinc, the cell potential of the zinc electrode is 0.76 positive. Now, the standard half cell potential for the oxidation of zinc is 0.76. It's a positive sign. This is a forward reaction. This is going this way. Zinc is becoming zinc 2 plus 2 electrons, and therefore it's a positive value. However, if you take this reaction and you reverse it, meaning 2 electrons and zinc will combine to form zinc solid. Like if you go in the reverse direction, if the forward direction is positive, then the reverse direction is negative for the E cell. Okay, so that means here's that reaction where zinc is being reduced here. Zinc is combining with the 2 electrons to become zinc solid, right? Solid zinc. So this 0.76, that's positive. You flip the sign and you have a reduction potential of negative 0.76 volts. Okay, so that is what the difference in sign really means. Oxidation for zinc is positive. Reduction for zinc is a negative voltage. Okay, the cell potential for zinc, for the reduction of zinc, is negative. Okay, so in this particular case where you plug in zinc to the hydrogen electrode, the electrons are going to flow from zinc to hydrogen. Okay, oxidizing zinc, giving you a positive 0.76 value. But if you were to reverse this reaction where zinc is going to become a solid again, you just have to flip the sign and make it a negative value because it's the reverse direction. Okay, now when you plug in the copper electrode, same situation, just the other side of the standard hydrogen electrode is going to be a copper electrode. Okay, since the voltage of the standard hydrogen electrode is 0, electrons are still going to flow from copper to the hydrogen. Okay, however, the oxidation of copper, here this is copper, gives us an actual negative value. Okay, the standard half potential or the standard cell potential for the half cell where the copper is the electrode, this number is a negative value, 0.34 volts. Okay, that means for the reduction of copper, when you flip the sign, it's going to be a positive value. This is the opposite of what happened at the zinc. In the forward reaction for copper, you got a negative value. This is for the oxidation of copper. Oxidation of copper. Copper losing electrons gives you a negative half cell potential, okay? But if copper were to gain electrons, meaning copper and two electrons would combine, so this is the reverse reaction from the top. This is the forward reaction here. This is the reverse reaction. If you were to reverse copper's oxidation, which means you have reduction, reverse of oxidation is reduction, right? The sign flips, and now copper's reduction potential is 0.34 volts positive. So zinc's reduction potential was negative. This is reduction of zinc was negative, and copper's reduction potential was positive. Now, the reason that I'm focusing on the signs is because when you get a table, okay, the table will have positive and negative values both. And the table is going to be full of standard cell potentials for reduction equations. And if you have a more positive value for your reduction potential, that means you are more likely to accept electrons. If you have a negative value, you are more likely to give up your electrons and become oxidized. Okay, so here is the table full of reduction potentials. These are all reduction equations. These are all metal ions accepting electrons and becoming reduced into their solid form. Okay, or hydrogen or any species accepting electrons and becoming in their reduced form. Okay, so let's look at the two metals that we are examining here, copper and zinc. They have boxes around them. So look, this is a reduction equation for copper. Copper 2 plus 2 electrons becomes solid copper. That's a positive value. Zinc becoming reduced, zinc 2 plus 2 electrons becoming zinc solid, that's a negative value. Things that are below the standard hydrogen electrode and have negative standard reduction potentials are more likely to get oxidized compared to things that have positive values compared to the standard hydrogen electrode potential. They are more likely to get reduced. You can actually kind of think of it intuitively as charge. Like you have more negativity in you, you want to give it away. If you are more positive, then you want to accept electrons and become reduced. Okay, so if you are trying to get to a place where you are like a zero, if you're more negative, you got to get rid of the electrons, right? Because the electrons are what's making you negative. And if you are more positive and you're trying to get to a zero, you want to accept electrons to become positive. Okay, so you accept electrons to cancel out that positivity. So it's kind of it's not really a, quantitative way to think about it. It's more like a conceptual understanding of why certain things undergo reduction versus why certain things undergo oxidation. If you're more negative, you are likely to go in the direction of oxidation. And if you are more positive, you are likely to accept electrons and become reduced. Okay? So these things will become reduced. They like being reduced, and these things on the bottom, they like being oxidized. Okay, if you are something that is going to get oxidized, that means you are a reducing agent. You are the agent that brings the reduction with you. And if you are something that gets reduced, then you are a strong oxidizing agent, meaning you are the one that is responsible for taking the electrons from the thing that is becoming oxidized. Okay, so since this is a table of all reduction reactions, it's the reverse of these reactions that will be oxidation, okay? So in order for you to check for zinc's oxidation, you would have to go this way, zinc becoming zinc 2 plus 2 electrons, that is oxidation, and the reduction number here, 0.76, you gotta flip the sign on this and say that the oxidation direction gives you a 0.76 potential for your half cell for oxidation. If you reverse the reaction, flip the sign. It's basic principle of chemistry. Reversing the reaction flips the sign. Same for enthalpy, same for free energy, and same for entropy, and same for E cell. Okay? Reverse the reaction, flip the sign. Not same for equilibrium because you have to like invert it, but everything else the same. Okay? Now, this part I couldn't go over in class, but it's very simple. This is how to actually calculate the standard cell potential of your galvanic cell. So now I'm talking about two half cells, each with one electrode on each side. One of them is undergoing oxidation, one of them is undergoing reduction. And you want to figure out, if you didn't have a voltmeter and it wasn't an experiment, if you just have the half cells, if you just have the equations for the half cells, how do you figure out the actual standard cell potential of your reaction? Okay, so basically you would have two beakers. In one of them would be some metal, right? And on the other one, it would be a different metal or some kind of aqueous compound, because it doesn't always have to be a metal, but the most common one is a metal. So you're trying to figure out what is your E cell, and you also need a salt bridge. Here's your salt bridge. So let's say the green one is the one that is undergoing oxidation. This is oxidation, this is your anode. And the blue one is the one undergoing reduction. This is reduction, and this is your cathode. Okay, so I want to figure out what is this number right here. And what you can do is you can use the table to get the value for this one. What is E ox and what is E reduction? We need the standard potential for the half cell. We need the standard potential for this side. And the difference between them will give you the cell potential for the whole cell. So this is your goal. Okay, what is this value? So here's the equation to do that. The standard cell potential for your galvanico-voltaic cell is equal to the half cell potential of your anode plus the half cell potential of your cathode. Okay, now some of your textbooks might write this differently. E cell equals E of the anode minus the E of the cathode. Nope, flip that. E of the cathode minus the E of the anode. Okay, it's literally the same thing. You just have to take the values from the reduction potentials table and do the work. Okay, or they might write this is E of the reduction and minus E of the ox. I find personally this one to be easier because you're just, adding two things together instead of remembering negative signs and whatnot, because the anode can be negative and it often is negative. Okay, so 1 second, 5 minutes. Oh, good. All right, I'm making a video for you guys. No worries. Okay, so you have your E cell. Here's something that you do have to remember, however, okay? Since you are looking for the oxidation potential and the table is full of reduction potentials, just flip the sign on the thing that is being oxidized. Okay, so you just have to remember that is oxidation and flip the sign. Since the standard half cell potentials are listed only for reduction half reactions, the half cell reaction potential for oxidation can be obtained by simply changing the sign of the reduction potential. So zinc becoming reduced is negative 0.76. Zinc becoming oxidized is positive 0.76. Okay, super easy. All right. Now, let's actually take those values and go back to our galvanic cell. So I have 0.34 for copper being reduced and 0.76 volts positive for zinc being oxidized. If it's negative for reduction, positive for oxidation. I want to go back to our very first cell, right here. So I had a voltmeter here in this picture that gave me 1.10 volts for my E cell. Okay, if E cell is equal to half cell of the oxidation plus this, the reduction, half cell potential for the reduction equation, let's see if we can get the 1.10. For zinc, this is oxidation. Okay, zinc is the thing that is being oxidized at the anode. So oxidation, the reduction was negative 0.76, the oxidation is positive 0.76 volts. Plus, for the copper, where reduction is happening, the half cell potential was 0.34 volts. 34 volts. So 0.76 plus 0.34 actually gives us 1.10 volts. Okay, so that is how this number came about. Okay, E ox plus E reduction, just have to flip the sign for the oxidation. Reverse the reaction, flip the sign. Okay,